Good morning, everyone. Welcome to the first workshop on trigonometry for people on the go. And I am Professor Simon. I am being accompanied by Professor Vicky Flanders here. We're going to duo a few quick topics in trig that always help in just about every bit of trig that you run into. And at the end, if you have questions about some other things, I know I have a few minutes. Vicky, you may not, but I mean, I can still hang out for questions too. But as always, I have to start the traditional way. Are you ready?
I'm ready.
Okay, so dad joke of the day. You know, I always walk through Walmart and have to talk to the cashiers, and they're always amazed by my job. I tell them I'm a math teacher, right? And I don't mean to brag, but they always check me out.
Nice. That's funny.
Yeah. All right, so dad joke out the way. The topics list. Vic, why don't you go ahead and share
Okay.
your daily Bob?
There you go. Blank screen for us to work on.
Yep. So the topics that I just sort of picked these off the top of my head as things that come up a lot throughout all of the different sections of trig. Wait, I gotta hit annotate. We're unit circle. And that includes all of the memorized values of the trig ratios that you need to know of the important values around the unit circle. Identities. There are several basic and a few advanced identities that are just paramount when it comes to not only getting through trigonometry, but as you'll find, pretty much every other subject after trig that uses trigonometry is going to interact with the trig with identities. So for example, calculus is riddled with trigonometry because of the way they overlap. And identities is the way that trigonometry can easily be simplified and communicate with the rest of the mathematical world. And then inverses. Inverse trig is important, and I find to be one of the topics that's either less hit upon or just less mastered in a lot of student situations. And inverse trig is extremely important if you ever have to find values or find angles in given situations where you're solving for something either in the real world or you're trying to get through a calculus class or whatever. So these are the three topics that I find sort of at this entry level for a first workshop would be good to sort of just hit again, even if you've hit them before. Okay. Vic, why don't you grab that and we can scroll it.
Got it?
Okay. Do you want to go first or?
No, you drive it.
All righty.
I'm sorry, I hate to interrupt you guys,
No, go
but
ahead.
after you go over this, would there be a time for us to ask particular questions on particular topics that we may have had? Because I wrote down some things that I struggle with, and I just want to make sure that I have all my ducks in a row before
I
you do
understand.
that.
Yeah, that's what I was saying at the beginning there. After we're done with these three quick topics, I'll hang out for a few minutes as well.
Okay, perfect. Thank you.
Mhm.
And I'm sorry, I was in a
Don't be.
meeting at work where you first started, so I'm going back and forth.
Don't be sorry.
Thank you.
All right, Vic.
Oh, let me okay, there we go.
Okay, so whenever you hear somebody say the unit circle, the first thing that should come to mind is a circle centered at the origin with a radius of 1. I don't think I could draw one that well ever again.
Good. You're right. Pretty good.
So then the way trig interacts with a unit circle is that you have some angle of rotation, theta, on a terminal side that can be considered a radius of the unit circle. Since it's a radius of the unit circle, of course, it has length 1. And then from there, I can take the coordinates that are actually on the unit circle itself, x and y, and make them trigonometrically meaningful. Okay? So in other words, what I end up doing is I end up drawing a right triangle where the height of that triangle is y and the base of the triangle is x. And of course, just like the equation of the unit circle suggests, x squared plus y squared equals 1. Not only from the Pythagorean theorem of that right triangle, but also that is the equation for all of the points that exist on this unit circle. But now also, if you apply trigonometry to this unit circle, I'm then able to define y as equal to the sine of the angle and x as equal to the cosine of the angle. And that's because of the way the trigonometry is opposite over hypotenuse and adjacent over hypotenuse. Technically, what I'm doing is y over 1 and x over 1, because that's adjacent over hypotenuse, opposite over hypotenuse. But of course, anything over 1, I don't need to write that as such. So then another thing that this connects is that the actual coordinates on a unit circle can be described using the angle itself. So for example, if I were to have the unit circle here and I were to have some ray intersecting the unit circle, and I said that that ray was rotated by 105 degrees, let's say, then I could ask, what are the coordinates of this point? Right? Given that this is, of course, the unit circle. Well, that would be easy enough to calculate using what we've just talked about. I could then say that x is equal to the cosine of 105 degrees, which make sure your calculator is in degree mode. I have negative 0.259. And of course, the y would be the sine of this. Which I have 0.966. So then notice the coordinates here, basically negative 0.3 and I'll just say 0.96. So it's not exactly 1. Notice how that makes sense for being in quadrant 2, right? Quadrant 2 should have a negative x value and a positive y value. Okay, so that's the connection of how the trigonometry is going to work, not only with a physical location, but also with the way the quadrants rotate. Vic, go ahead and grab that and we can scroll it.
Yeah, I'm ready to do that right now. All right, got it.
Okay. Nice.
Okay.
Okay, so then
I have a question. I'm sorry.
Yeah, go ahead.
Can you scroll back up? So I have and this may be crazy, but on there you made it point negative 0.3, and then on y you made it 9.96. Why wouldn't y be 0.97?
Oh,
Why wouldn't we
yeah,
move?
you're right. That technically could have been 0.97. My bad.
Okay. Okay. I just want to make sure because you know, math lab is so temperamental. Like if you don't put it exactly the way they say to put it, it's wrong. And I guess that's why I'm getting caught up with in some of the confusion of things. But thank
Sorry
you.
about that. I was just writing.
No
fast.
problem.
Okay, go ahead and scroll a bit. Okay, so then the next bit that you want to merge in there is the important values that go along with the special angles. Okay, so when it comes to remembering the sine, cosine, and tangent of special angles, let me start with the basic few, right? So that's going to be the sine, cosine, and tangent. And then I've got the 7 special angles that are always regarded as important. So I've got 0 degrees, I've got 30 degrees, I've got 45 degrees, 60 degrees, then 90 degrees. Then I'll go ahead and just throw down the 180 and the 270. Okay, now one way to, of course, see that the values that I'm about to write are what they are would be to write down triangles that these things fit in. But what I want to show you real quick here is a faster way to remember these if you want to, always just have a way of writing these down real quick. So here's one way that you can do this. What I do is I start by counting. Okay. So here's what I do. I do 0, 1, 2, 3, 4, like this. Okay. So that makes sense, right? I'm just counting. For each one of these, take the square root, square root, square root, square root, square root, square root. And for each one, divide by 2. Like this. Now, a few of these can be simplified. What's the square root of 0? Anybody? I see Brittany trying to say it.
Yeah, Brittany, you're muted.
0.
It is 0,
Good.
right? What about the square root of 1 and the square root of 4?
1 and 4.
1 and
2.
2, right? Yeah. So let me go back and simplify those. The square root of 0, whoops. I'm hitting too many. So that was 0, right? 1 and 2. But of course, anything 0 divided by anything is still 0, and 2 over 2 is 1. So I can simplify these even a little bit more. Right? So I have 0 and then I have 1 here. And what that gives me is the sine value for 0, 30, 45, 60, and 90 degrees. Right there. Those are all completely simplified versions. 180 is on the same line as 0. So it also has 0 for the sine. 270 is on the same line as 90. One of them, 90 is up, 270 is down. So 270 would then, of course, be -1. You can alternate the 0. You can alternate the values according to which ones are complementary. Okay, so here's a crossover with what the next topic. A big major identity is that the sine of any angle is going to be equal to the cosine of its complement. And this is because of the way our right triangles are defined. 2 complementary angles that add up to 90 both fit in a right triangle, but they have opposite and adjacent that switch. So the sine and the cosine for any angles that add up to 90 also switch. So for example, this is what I mean. If you take a look at 60 and 30 degrees, right, the sine and cosine values switch. 45 is his own complement because 45 plus 45 is 90. So that's why the sine and cosine are equal. And then also notice 0 and 90 are complements. So those would also switch with a 1 and a 0. So you do a lot of this little crisscrossing here to get the next level. And then, of course, just like the level above, 180 is on the same line as 0. 270 is on the same line as 90. So those two match those two. To finish up, tangent is going to be a division. 0 divided by 1, right, is 0. 1/2 divided by square root of 3 is going to be 1 over square root of 3. Anything over itself is 1. Square root of 3 divided by 1 is just square root of 3. 1 divided by 0 is undefined. 0 divided by anything is 0. Negative 1 divided by 0 is again undefined. Okay, so then how does this link back to the unit circle? These become the important angles all the way around. Maybe I can do it a couple times. That one's not too bad. So I've got those 3 angles in the first quadrant here, right? I've got the 30, 45, and 60, but then I've also got 0 and 90 on my axes. Okay, so the way that this information encodes onto the unit circle so that you don't have to memorize a whole bunch of stuff is you literally just memorize the point locations of each of these dots, if that's the way you choose to do it. Some people prefer to memorize the chart and then translate it, whatever. It's whatever way works best for you. So then remember, though, from before, the coordinates are always the cosine and then the sine. Okay, so then this first point right here and on the x-axis is going to have the point 1 comma 0. Next, this point right here would be square root of 3 over 2 comma 1 over 2, right? Then square root of 2 over 2, square root of 2 over 2. Then 1/2 and square root of 3 over 2. And then right here at 90 degrees, you would have the point 0, 1. Notice how the 0 and 90 degrees actually makes sense to the circle, right? Because that's an actual point on an axis there, right? We know it's 0x and just full radius 1 with the y. Okay, but then I can also continue. I can continue into the subsequent quadrants using reference angles. So for example, if I take this angle right here, right? If I say that the angle here is 45 degrees, then the other angle here is 135 degrees. And the point of that one is going to be negative square root of 2 over 2 comma square root of 2 over 2. And that's because it's symmetric across the circle with the point straight across from it. So in other words, it's symmetric with this point right here. Therefore, not only have I remembered 45 degrees sine and cosine, but now I also have 135, right? Using the symmetry there, I can keep the coordinates, and notice the only thing that changed was the SIGN of my X coordinate. So whenever someone says I'm memorizing the unit circle, this is what they mean. There's actually angles from each quadrant based off of the 3 main ones. Ooh, surgical maneuver there. Right, so in other words, there's 3 in each. And these are the values that are constantly going to be asked of you. Every single one of these pair go off of being either the closest to the x-axis, the middle, or the closest to the y-axis. Okay, so every time you're close to the y-axis, notice the x value is 1/2 and the y value is square root of 3/2. Except over here it would be negative 1/2 square root of 3/2. All right, and then right here it would be negative 1/2 negative square root of 3/2. And then right here, it would be just 1/2 and negative square root of 3/2. So I'm just using the appropriate SIGNs given each individual quadrant. If you're close to the y-axis, the 1/2 is your x and the square root of 3/2 is your y. If I get close to the x-axis, notice it flip-flops. So then everything that's based off of those, right, square root of 3/2, negative 1/2 would be this one. Negative square root of 3/2, negative 1/2 would be this one, right here, right here. What would this one be right here?
It negative square root over 2.
Negative square root of 3/2, right?
I'm sorry, negative square
Right.
root of 3/2 and negative, I'm sorry, 1/2, just 1/2.
1/2, right. Okay.
I kind of cheated. I printed out the unit circle thing on my, I'm printing it in the background on my other
I
phone.
understand.
Is it okay if I screenshot what you're doing just so that I can have it for later?
No, that's fine. We'll also
Okay.
have, that's why she's saving these though. Go ahead and cut it. That's what she's saving.
What, do you want to finish?
What's
Do
that?
you want to finish the middle one in the third quadrant and fourth quadrant?
Okay, Miss Neurotic. I'll finish it.
Yeah.
So can I do those? Just making sure I have the right thing. It's negative square root of 2/2 and the same for y.
And then what about the fourth quadrant?
It's negative 1/2 and negative.
Nope.
Nope.
Okay.
Right here.
See. Wait a second.
This one in the middle.
Oh, this one on the, okay, let me go over there. I'm sorry, it's a positive square root of 2/2 and a negative square root of 2/2.
Yep.
Yep. Okay, I just want to say one thing before I snip it. So all these points here have all the angles over here in the chart, or they have a reference angle. So in other words, you know, your first quadrant is 30 degrees, 45 degrees, 60 degrees. And then in the second quadrant, okay, well, these angles are going to have those as reference angles. So as we're rotating here into the second quadrant, it's going to be 120, because that's going to have a 60-degree reference angle. 135 degrees, it's going to have a 45-degree reference angle. And this is going to be 150, has a 30-degree reference angle. You guys see what we're saying? And you just keep on going along the circle in that fashion. And you have those, yeah. So you want to write something else for a snip?
Yeah, go ahead and snip that, Vic, and
Okay.
then you can work that example to go along with what you were saying.
Okay. You want me to snip it first and then work the
Yeah,
example?
snip it and then you'll be able to write on it.
Gotcha. Gotcha.
Well, Ross,
Got it.
I can notify your instructor about it if you want. I don't know what they had, you know, going on or whatever, but I certainly don't mind sending an email, or, you know, also Miss Stacy, running the main ALC will definitely be in contact if you request it.
Please do there, Mr. Simon. I appreciate that.
Who is your instructor?
Professor Forrest.
Oh,
All right. So all of this unit circle is very valuable, and gives us the sine, cosine, tangent, and of course secant, cosecant, cotangent are just the reciprocals of the, you know, sine, cosine, tangent. So we can get all 6 trig functions of any of these angles on here, and these angles are pretty common. They're called special. These 30, 45, 60 degrees are called special angles. And because they have these exact values, and we always want to have the exact value for the sine, cosine, and tangent. We really don't like getting the decimal approximation. We get into some rounding errors if we use too many rounding values. So these angles come up quite often. They have exact values for the 6 trigonometric functions. So for example, if I want to find cosine of 240 degrees, all right, where is 240 degrees? Well, it's in quadrant 3. Okay. And let me see, let me use just a different color. Let me just use maybe orange here. 240 degrees is in the 3rd quadrant, like I said, but with a 60-degree reference angle. And it would be right here. Right here is 200. Oh, it's turned out to be green, but 240 degrees. Okay. And that's because this here is your reference angle 60 degrees. Okay, your reference angle is always the angle made with the x-axis. Okay, so what do I know here? Well, it's going to be the x value. What's the x value? -1/2. Now, all that you really have to know, if you have this little chart here, you could just go to 60 degrees. You see right here, 1/2, but 240 has a reference angle of 60, but 240 is in quad 3. And in quad 3, cosine is negative because the x value is negative, because cosine is the x value on the unit circle. So there's lots of things that kind of, make sense here and come into play and is very logical. Do you have any questions? You guys are good? Everybody's good? Okay, you want to do another one? How about somebody do this one?
Wait, I was
What?
going to say, Vic, the
Okay.
way I also see it is, even if you're not even thinking of the unit circle right away,
Yeah.
you know that your angle is in quadrant 3, let's say, because I can see 240 is bigger than 180. Then you have to know that in quadrant 3, the way to find the reference angle is to do that angle minus 180, right? If it's in
Yep.
quadrant 2, it's 180 minus the angle. If it's in quadrant 4, it's 360 minus the angle, right? In this case, I get the 60 degrees, right? And then that immediately gives me which one from the chart I should be plucking.
Yep. And that works for all of them, guys.
Mhm.
That works for all of these angles on the unit circle that we pointed out here. They all have the 30, 45, or 60-degree reference angle, or they actually land on the axis. So this is very common. We ask these questions all the time in trigonometry class. I'm sure you have this on your final.
Vicki, add the radian counterparts too, since you've
Oh,
already.
yeah. Do you want me to just label the whole unit circle?
Just draw a line underneath of the chart and add the
Oh, okay. I see what you're saying. So 0 is 0 radians. 30 degrees is pi over 6 radians. 45 degrees is pi over 2.
Nope.
Pi over
Pi
4.
over 4.
I know. I'm going,
You're
excuse
going
me.
too fast.
I'm
I
just
know,
excited
I'm
that I can
already at the
actually talk
90
Trig.
degrees. All right, pi over 3. I was thinking about saying something and I didn't say it. Pi over 2, pi, 3 pi over 2. So what I was thinking, and I shouldn't be thinking something differently than what I'm writing, and that caused me to make a mistake. But what I was thinking was that, how do I know this really quickly? Well, I always associate pi, 180 degrees equals pi. And then I just think about, well, 30 degrees is 180 divided by 6. So it's pi divided by 6. 45 degrees is 180 divided by 4. So it's pi over 4. 60 degrees is 180 divided by 3. So it's pi over 3. 90 degrees is pi 180 divided by 2. So it's pi over 2. So it's really easy when you think about pi being 180 degrees, 2 pi being 360 degrees. Very easy to think about it that way. Okay.
Right.
So,
Yeah. I always think of pi as 180, and it's kind of like the multiplication facts of 18, if you will, right? 3 times 6 is 18. 2 times 9 is 18.
Exactly.
And that goes for the 180 for that's just how my brain always sees it,
Yeah. And it's a good way. It's a good way to think about it that way. And it's, yeah. And that's how I think about it as well. So think about, you know, you put just pi being 180 degrees and you can make all your little conversions very quickly in your head.
So Vicky, next let's talk about the identities. Let's list out the
Okay,
basic ones.
Yeah, I'll do the basic ones, and then I can derive the Pythagorean ones, show them how you get those.
Well, I mean, the derivation's great. We're trying to do it on the go. So let's list them out.
Okay.
Let's work a problem where we use it to find an angle, like the value of one given another.
Okay. All right, gotcha. All right. So I'm going to start off. Let's see. Let's wait, my pen's I've switched my pen out. This one's dead. I use them. I'll switch them out 3 or 4 times a day. That's how much I use it. All right. Yeah. Identities. So let's start off with the ones, the reciprocal ones. Those you should know, right?
Mm-hmm.
The fact that sine theta is 1 over cosecant theta, which also means that cosecant theta is 1 over sine theta. So you can remember it either way. Cosine theta.
There's a third way too.
Is 1 over secant theta. Oh yeah, I got you. And then secant theta is 1 over cosine theta, which also means that because they're reciprocals, you multiply them to get 1.
And the reason why I brought that up, guys, is to be sure later on in the 3rd unit of trig, there's a whole section on simplifying things using identities. And a lot of times the trig functions are multiplied together. And so if you happen to notice that you have a pair of reciprocals multiplied, as those last 3 in the last column there stimulates, they can easily simplify when they multiply reciprocals.
Yeah. So here's your 6 basic, you know, these are the reciprocal. Let me kind of reciprocal. All right. And then we have, let's do the quotient ones, because you can write, let me change colors. You can write tangent as sine theta, you know, over cosine theta. So tangent theta is sine theta over cosine theta.
Which
and
I
that
used
means
in the chart.
Oh yeah, that's how we used in. So we had to know that. And because cotangent theta is a reciprocal of tangent theta, we write, well, you reciprocate sine over cosine to be cosine over sine.
And the
Okay.
alternates of those where you multiply, right?
Yeah, what you want to do.
Tangent times cosine.
So, well, let me write, yeah. And so by just all we're doing is manipulating this equation. So we can write cosine theta times tangent theta is sine theta. Same thing here. Sine theta times cotangent theta is cosine theta.
Right. Now it seems like a lot to remember, but if you remember the basic ones, like everything that we're putting on the left, like for example, tangent is 1 over cotangent. Remember that one. Tangent is sine over cosine. Remember that one. You can always change them into these alternate forms. We're just trying to show you some alternatives so that it will spark those ideas whenever you're approaching these things.
Okay. So let's go over the Pythagorean ones. Sine squared theta plus cosine squared theta equals 1. And we can write this, you know, we can solve it for sine squared theta. We're just manipulating the equation. Or cosine squared theta is 1 minus sine squared theta. So we got 3 ways to write that one identity.
Mm-hmm.
And then real quick, mostly all students remember this one. It's very easy to remember, but they have trouble remembering the other 2, just like me. So what I'm going to do, I'm going to show you something real quick. All I do is divide by sine squared theta. Both sides, making sure you distribute. Division is also distributed like multiplication. And so what do I end up with? I end up with 1 plus cotangent squared theta is what? Cosecant squared theta. And I can rearrange that. 1 equaling to cosecant squared theta minus cotangent squared theta, or also cotangent squared theta is equal to cosecant squared theta minus 1. Or I can go back to my original Pythagorean identity that I have here. And I could also derive these by the Pythagorean theorem, but I didn't do that. And now I could divide everything by cosine squared theta. And I'll get that tangent squared theta plus 1 is secant squared theta. I can rearrange that. 1 is equal to secant squared theta minus tangent squared theta. And that is also what? Tangent squared theta could be equal to secant squared theta minus 1. So there's these different, 3 different identities, and they can each be written in 3 different ways. And these are called Pythagorean identities. Okay, Dave, you want to go ahead and work a problem? Because I'm not sure exactly what problem you want to work. So it'll be okay if you just work it. Did he leave? He left. All right, I think he wanted me to work a problem with using the identities, finding a trig, another, let me see. So let me just write example here. I hope this is what he meant. I could say find cosine theta. Well, there he is. I don't know exactly what you want me to do here, Dave. Suppose I say find cosine theta.
Deal with the baby.
Okay, I could say find cosine theta
if cotangent is 7.
Yeah, if cotangent theta is 7.
That's what I was thinking of, yeah. Or
And theta,
actually find all 5 if cotangent theta is.
Okay,
yeah.
Let's say that. Find the remaining trig functions of theta if cotangent theta equals 7. Do you want to say theta is in quad 1? Or is it assumed?
3.
Okay. If theta.
Well, you don't have to put the if. Just put. Oh, okay. Yeah, I guess you could do that. I was gonna say do this.
Okay. Go ahead and erase that. I'll put that.
Everybody, that little e means exists in or is an element of. So in other words, theta is inside of quadrant 3 is the symbols there.
Okay. Now, do you want them?
The symbols.
Do you want them only to use identities or?
Correct. Yeah. That's
okay. Because you could go to a graph. You could go to the court, but let's just use identities. Okay.
Right.
Now, I'm going to make a few notes first. Okay. So my notes. Because theta is in quadrant 3, what do I know from the start? Quadrant 3, cosine theta is, okay, the x, remember it has to do with the x value. It is what? Negative. And sine theta is also negative because it's the y value. But the tangent of theta is what? It's positive. And I could have written that first, the positive one. Right, now the reciprocals are going to have the same SIGN, okay? So I need to know that from the beginning because I might have a square root come up with a plus or minus. And I have to say, well, is it the plus or is it the minus? This can't be both. I got to make a decision. And my decision is going to be based on the fact that theta is in quad 3, okay? Alrighty, so let's see. Cotangent of theta is equal to 7, okay? Well, I have a Pythagorean identity that says right here, 1 plus cotangent squared theta equals cosecant squared theta. I'll be able to find cosecant squared theta. But I just thought about something. Well, if cotangent theta is 7, what is tangent theta? 1/7, right? And is it positive 1/7? Yes, because it's in quad 3, and I'm just making sure my cotangent theta is positive 7, it's supposed to be. Okay, so that's one of my 5 remaining trig functions. Now let's go ahead and I could use the 1/7, but I had to achieve that myself, so I'd rather not, but I could. But I'm just going to go ahead and use the 1 plus cotangent squared theta equals cosecant squared theta. So I'm going to go over here. 1 plus cotangent squared theta equals cosecant squared theta. So 1 plus 7 squared is equal to cosecant squared theta. So this is what? 1 plus 49, which is what? 50.
Last time I checked, it was 50.
So I get that the square root of 50, or plus or minus, I should say, is cosecant of theta. Now I can break that square root down or simplify it. 25 times 2, so that's 5 square root of 2. You definitely want to do that. And is it positive or negative? Well, look right here. Sine theta, it says is negative, so that means what? Cosecant is also going to be negative. Good job. So I know that tangent of theta is 1/7. Negative 5 square root of 2 is a cosecant theta. This means that sine theta is negative 1/5 square root of 2. You make them rationalize, Dave?
I tell them that I take it either way, but you know,
Okay.
it's also worth
In math-
mentioning that later on when you do like double angle and things like that, they have to have common denominators and stuff. So
Yeah.
it's good to be able to do the rationalization.
So if I rationalize it, I get negative square root of 2 over 10.
Yeah.
So either way, rationalizing it or not. All right, so I have 3 of them. How can I get the others?
You actually have
Okay, well,
4, right?
1,
You have cotangent.
2, 3, 4. Okay, yeah, so I need to get 2 more. What do I need to get? I need to get secant and cosine, right?
Cosine.
Now,
It's cosine, yeah. Mm-hmm.
yeah, secant and cosine. So
Quotient.
what can I do? So I'm trying not to use something that I had to achieve, but I won't be able to. I have to use a value that I got. So you might want to double check your answers, but you guys are all watching me, so I know my answers are right. But if I did it by myself, I might want to double check it. So let's use maybe cotangent theta is cosine over sine. Maybe let's do that. Okay. So let's.
But use
let's
the alternate form of it.
Meaning what?
Because you're finding cosine, right? So you
Yeah.
have that alternate form there where sine theta times cotangent equals cosine.
Oh yeah, there. Okay. Well, I always like it where I memorize it from.
Okay.
So I'm gonna write down that cotangent theta is cosine theta over sine theta.
Right.
So cotangent theta is 7. That's cosine theta over sine theta. Sine theta is negative 1/5 square root of 2. So 7 is what? Negative 5 square root of 2 times cosine theta. So 7 over negative 5 square root of 2 is cosine theta. And you can rationalize it, or negative 7 over 5 square root of 2. Is it supposed to be negative? And the answer is what? Yes, right? So I can also rationalize it. Then I could also say that secant theta is reciprocal. So it's negative 5 square root of 2 over 7. All right, I think I have all 6, right? I was given cotangent, got tangent, sine, cosecant,
Yep.
cosine, and secant. And there we go.
Yep, that's using identities.
Yep. So I used the Pythagorean identity. I used the quotient identity. I could have used the sine squared theta plus cosine squared theta equals 1 and used sine theta, but I used it. What did I use? I used cosine theta. No, I forget what I did. Anyhow, I used the quotient identity instead. So
Right.
anyway, all righty, Dave, you're up.
Okay, inverses.
You guys said that you upload this up to somewhere so we can have copies of it.
Yep. And this session's being recorded as well.
Okay, perfect. Thank you.
Absolutely. So for the paper and the recording, I guess what we'll do is we'll give it to Miss Stacy at the ALC director there, and then she'll probably just supply it to whoever. Or you know what, Vic, let me
Yeah, it won't,
let's do this. I'm gonna put my email in the chat, and
Okay.
Miss Flanders is too, and you can email either one of us. And anytime you need help, you can email either one of us too.
Thank you. I appreciate that.
Yep, there it is.
Not a problem. Okay, inverses. So inverse trigonometry is the idea that I can take some sort of trig operation of an angle, which is equal to a ratio, and then reverse it. Much like the idea where when you originally learned addition, I can reverse that into a subtraction, right? C minus B would equal A. The idea that all operators in math have a symmetrical opposite to them is paramount in just about every field of study, because you need to be able to solve, you need to be able to undo things. The difference with trig is that it looks different than, say, addition turning into subtraction. And a lot of people forget that the trig functions themselves, the trig operators, are just that. They're operators, things that do their own action. Okay. So I can take any trig function and rewrite it as an inverse trig, a lot of times symbolized with a -1 of whatever trig function that is. And notice you do an inverse trig on a ratio, and the result is an angle. Although eventually later on, these become just values, like the inverse trig of some value, equals something. But another way of interpreting this, by the way, is instead of an angle, you can also call these arcs. This is an angle, or it's an arc. In other words, an arc meaning a piece of a circle. Okay. So a lot of times, because of the fact that the answer to an inverse trig function results in an angle, which is also considered an arc, sometimes they also call it arc functions. So instead of writing it with the -1, I could do arc whatever the trig is of the ratio would give me the angle. Okay. So that's just because of the object that results from it. So for example, since I know that the sine of 30 degrees is equal to 1/2, then I can define the inverse sine of 1/2 to be 30 degrees. Or in other words, I could say arc sine of 1/2. I almost did it myself. Is 30 degrees. Okay. This is the basic idea of inverse trig right here. The ability to find an angle, to find an arc piece of a circle by using a ratio of sides in a triangle setup. All right, Vic, copy and scroll.
Okay. All right, got it.
Okay.
Okay.
Nice. Okay.
Do you want to keep that showing, or you want me to
No, it's fine.
Okay.
So then let's let's get some further definitions here. All right. So remember that all students take crap, right? Those are the symbolizing of what is positive in each quadrant, right? So in quadrant 1, all are positive. In quadrant 2, sine is positive. In quadrant 3, tangent is positive. And in quadrant 4, cosine is positive, right? Everything else except for their reciprocals in each of those quadrants is a negative value. So what you have to remember is what it means to ask about these ratios when we're doing these inverses, okay? So for example, if I were to ask a question, what is the arc sine of 1/2, like we just did? I showed you the actual definition of that is the 30 degrees. Notice 30 degrees is a quadrant 1 answer. And notice in your calculator, if you hit second and sine, you'll get the little inverse sine operation. I don't know if y'all can see it on my camera or not. It's kind of dark. Second and sine gives you the inverse sine operator. And if you put in 0.5, it gives you the 30 degrees like what I have written here. Okay. Notice that it does not give you 150 degrees, which would be the quadrant 2 answer. It does not give you that. Okay, 150 degrees would be the 30-degree counterpart in quadrant 2. And the sine of 150 degrees is positive 1/2. However, the arc sine of 1/2, the inverse sine of 1/2, does not give 150 because we've defined it that way. Okay, it's very important to see that we've defined these functions as just that, functions. They can only give one answer to be considered a function. So even though 150 would be a correct answer to the question phrase like this, if I were to say sine theta equals 1/2, theta equals question mark, this question right here has the answers that theta is equal to 30 degrees or 150 degrees because of the way I phrased it. Okay, I didn't ask specifically what is the inverse sine. I said, hey, what angle has the sine ratio of 1/2? And so therefore now you can answer both. But arc sine at the top there is a calculation. This is something that needs to be defined as an individual operation, and therefore it can only have one answer. Okay, so then what you need to remember is which quadrants are used for which particular inverses. Okay, so these you need to remember. You need to remember that sine and tangent use quadrants 1 and 4. So inverse sine and inverse tangent use quadrants 1 and 4. And inverse cosine uses quadrants 1 and 2. Okay. Typically, we only run into the inverses of the three main ones, the sine, cosine, and tangent inverse. So these are the only ones that you truly have to mess with. Notice quadrant 3 is typically not even used in these kind of solutions. Okay. But it is important to remember this. So basically, what am I saying when I write these out? Okay, no problem, Justice. What am I saying? I'm saying that if I do inverse sine of a positive number, right? In fact, I'll just use positive right here. I'm going to get a quadrant 1 answer. If I do inverse sine of a negative number, I'm going to get a quadrant 4 answer, but I'm going to get the quadrant 4 answer as a negative acute. Okay, so for example, if I ask what is the arc sine of negative 1/2, I'm going to get negative 30 degrees. Even though 330 degrees is the same location, right? 330 degrees rotates all the way around to be the same as negative 30, right? Like this. This is negative 30 degrees. 330 is here. Arc sine of negative 1/2 is not going to give you the 330. It's going to give you negative 30 degrees, which technically they are equivalent, but numerically they're really not. Okay, so that's what sine and tangent both do. They both will give quadrant 1 for positives or quadrant 4 for negatives, and the quadrant 4 is going to be a negative acute. Okay, so inverse tangent of a positive is a quadrant 1. Inverse tangent of a negative is also quadrant 4, but in the form of a negative acute. But cosine is different. Inverse cosine of a positive still gives quadrant 1, because everything's positive in quadrant 1, right? But in quadrant 4, cosine is not negative. So therefore, if I want to do an inverse cosine of a negative number, I have to pick something else. And that's why I have the green border over there. Cosine is affiliated with quadrant 2. It's going to give me a quadrant 2 answer. So for example, if I ask, what is the arc cosine of negative 1/2? I'm going to have to go back to my chart and remember, hey, which angle had a cosine of 1/2? It was which acute angle? Which acute angle had a cosine that was 1/2? Anybody?
Anybody?
Which angle has a cosine of 1/2?
30 degrees.
No, that's the sine.
Okay.
It's 60, right? So inverse cosine of the negative 1/2 is going to give you the
Okay.
degree equivalent, but in quadrant 2. So that's 120, because 120 plus 60 is 180. And you can even check that in your calculator. If you hit second cosine for inverse cosine of negative 0.5, it'll slap out 120 degrees. Okay, so just some basic facts there about using these inverse functions. They are limited to certain quadrants, and that's so that they can actually be functions, and that's how your calculator is programmed to treat them as the calculation, and then you have to extrapolate. Okay. All right, Vic.
You ready for me to snip?
Yeah, grabbing. Let's go. Let's keep moving. I just want to hit a couple of more examples, and then
Okay.
and then simplify a complicated one, and then be done, so that we can answer questions.
Okay. I got it.
Okay. Clear.
Okay.
Yeah. Okay.
I never
So
know
then
how. Okay, there it is.
let's okay, so then because of the way these are defined, obviously one of the things is, if these are inverses, just like plus and minus, right? If I put +3 and -3 next to each other, they should wipe out, right? That's the whole idea of an inverse. So then, for example, if I put sine on top of, or inverse sine on top of sine, right, of some angle, does this equal the angle? Right? Do they wipe out and actually give me that theta back again? Well,
Sometimes.
again, what's that?
Sometimes.
Sometimes, yeah. See, that's the thing.
Does
Does
it?
it always give the same angle back? And the answer is no,
No, it doesn't.
because remember, as I was just saying, these are restricted, right? So this does equal theta, but if theta is in the quadrant 4 and 1 region, okay? So there's a big old if on that. It only does that reduction if that is true. Same thing goes for tangent, because tangent has the same restriction. And then cosine also is restricted, but remember, cosine was restricted to quadrants 1 and 2. So theta would be in between 0 and 180 degrees. Okay, so let me throw out a couple of examples to show you what happens when you try to, when this works and when it doesn't work. And you can punch these in your calculator and see. So for example, if I do the inverse tangent of the tangent of 58 degrees, that's going to give me 58 degrees back again. You can check that in your calculator. Hit second tan, then hit tangent again, 58, close both of your parentheses, and you'll see that it gives you that value back again. But however, if I were to do inverse tangent of 100 degrees, notice I will not get 100 back as an answer for this. 100 is not in that restricted area of tangent, okay? In fact, it's in a negative region for tangent. Notice 100 degrees is in quadrant 2, and in quadrant 2, tangent is negative. So right here, this tangent, this inverse tangent is acting on a negative number. Tangent of 100 just by itself is a negative value. So inverse tangent of a negative value, remember, is supposed to give me a quadrant 4 negative acute answer. Okay, so what that's going to do is that's going to give me something back from that quadrant 4 negative acute type of answer, right? Well, what's the reference angle here for 100 degrees? 100 degrees has a reference angle of 80, right? If I graph out 100, the reference angle over here is 80 degrees. And we're doing the inverse tangent of that. So it's going to be in quadrant 4 in this same region here. And it's got to be symmetric in size. Notice the negative 80 is right there. So that's what we're going to get. We're going to get negative 80 degrees for this. If you punch that in your calculator, inverse tangent of 100, you'll notice it gives you a negative 80 for the result. Okay, so you have to watch what's going on when you're doing these things. Let me throw out one more example here. What if I were to do the inverse cosine of 1300 degrees? Obviously, it's not going to give me the 1300, right? That's outside of the scope of the limitation on cosine there. It's definitely bigger than 180 degrees. Okay, so what I need to do is I need to figure out, first of all, which quadrant am I in and what my reference angle is. Okay, so 1300, right? The first thing I'm going to do is figure out what is coterminal with 1300, but is in between the 0 and 360, right? The way I do that is I divide 1300 divided by 360. It tells me 3.61. That tells me that I've got 3 full loops. 1, 2, 3 full loops. Okay. So then I subtract 3 and I have 0.61111. I'm going to hit times 360 again to see. And it tells me I have 220 left over. Okay. So then that's what I do from there. I know that 220 is in quadrant 3. So 220 goes to there. And then I can further get my reference angle. My reference angle is going to be this guy here, which I'm going to be doing 180, 220 minus 180 to get my reference angle. Right? I have 20 up and 20 down. That's going to be a 40-degree reference angle. Okay, so now, since I'm in quadrant 3, I know that cosine is a negative, right? I know that this right here is a negative number. Okay, go back to your rules. Cosine inverse acting on a negative number gives me a quadrant 2 answer straight out. So I'm going to take my reference angle 40 degrees and I'm going to put it in quadrant 2. So 40 degrees in quadrant 2 gives me my result here. 180 minus 40 is 140. So notice, if you were to type this in your calculator, the answer there is 140 degrees.
Professor Simon, I have a quick question. You
Go for
lost me after the 3.6. I don't know what to do with that to get to 220.
Oh, subtract the 3 because you're taking away the 3 loops.
Okay.
And then hit times 360 again to make it back to a full, one full rotation, times 360.
Okay, perfect. Thank you.
And I mean, there's other ways to do it. You could take the 1300 and just hit minus 360, minus 360, minus 360 until you get something smaller than 360. That's another way to do it. But if you have, 30 full rotations, it gets a little tedious at that point. But there's multiple ways of doing it.
And the reason you multiply it times 360 is that decimal 0.66, whatever it was, 0.661, whatever it was, it's a portion of a circle. So what portion of 360 degrees? You want to know that fraction is what portion of 360 degrees. So multiply it times 360, and that tells you the degree measurement, 220.
Okay, perfect. Thank you.
Okay, so that's how inverses work. Go ahead and snip it, Vic. That's how inverses work, interacting with their counterpart, right? Their inverted counterpart. You have to be careful that sometimes you can cancel them, like in the example,
got it.
58. And then other times you cannot cancel, and you must see where you're at for those. The only other thing about inverses is how they interact with a different trig function than their own counterpart. And I'll just do a quick example of that so that we can get a roll on here. Okay. So what I'm doing is I'm pulling one of the things here from the textbook that I use, the OpenStax textbook. Okay. So simplify this. The secant of the inverse sine of x over x plus 1. Now notice that the inverse sine is on the inside this time. The inverse is on the inside, okay? And it's acting on a ratio which comes from a triangle. Right now, we're just going to make the assumption that x is a positive number, okay? We're just going to go ahead and throw that in there. That does make the problem a certain restriction to the simpler field that we usually do in normal plane trigonometry here. Okay, there's other things that we can do about x being a negative, but then we have to actually segregate it and have more advanced cases. So typically, just to get practice in, what we do is we use mostly positive things. So then what does this do? If x is positive, notice that that ratio is going to be a positive. X over x plus 1 is going to be a positive ratio. So inverse sine on a positive ratio, this calculation just in here, right? This whole calculation here is going to equal a quadrant 1 angle. Okay? That right there is going to give me just some angle, right? and it's in quadrant 1. So in other words, I've got something like this. Theta is some angle in quadrant 1 such that the sine is x over x plus 1. That means I could label this side over here as x and the hypotenuse over here as x plus 1. Notice that triangle, the opposite over the hypotenuse is x over x plus 1, which would tell me that sine of theta is x over x plus 1, which is exactly what this thing on the inside here is requesting, that the inverse sine of that ratio be theta. Okay, so then the only thing left is I want to do secant of that theta. So that's really all we're answering here. We're finding out what the secant value is given this particular triangle that the sine value is x over x plus 1. Well, okay, to do that, I just need to have some sort of representative over here for the adjacent side. I'm going to say that it's capital A for a moment. Okay. So in other words, my secant is going to be whatever capital A is over x plus 1. Because, oh, I'm sorry, I did it backwards. Sorry, I did cosine. Whoopsie, whoopsie. It would be x plus 1 over whatever A is. Okay. So now I just need to figure out what is A when it comes to x. Well, I can use Pythagorean theorem for that. A squared plus x squared should be equal to x plus 1 squared. Okay. Therefore, a squared is equal to x plus 1 squared minus x squared, which I can actually simplify that a little bit. X squared plus 2x plus 1 minus x squared by foiling out x plus 1 times x plus 1. And notice my x squareds add out. So I'm left with a squared is equal to 2x plus 1. Okay, so what that tells me is that a is equal to the square root of 2x plus 1. Notice I chose the positive square root as well, because I know I'm in quadrant 1. That's important, which is, earlier when I chose x to be greater than 0, that was an important choice. That's why the square root is coming out to be positive. So then final answer here, I can say that the secant of the inverse sine of x over x plus 1 is equal to x plus 1 divided by the square root of 2x plus 1. Now, this was sort of an advanced example, but I want you to notice that even if they had given me numbers inside of that inverse sine, I could have followed the exact same process. And what I've just done is given you an advanced example of a process, not just an individual problem here. You can interact any normal trig on top of an inverse trig in this manner by drawing your own triangle, creating an angle, and then using the ratios and the identities that you know. Did you get it, Big?
Yep, I got it.
All right. Cool.
There
Well,
it
guys,
is.
that was all that I wanted to present. That was all the way through inverses there with some examples. Let me just point out real quick, in case you haven't already noticed, and maybe your instructor hasn't told you, or anybody watching this later on, I also have an entire YouTube series of lectures that I've created on, trig is one of the subjects, if you go to YouTube and search for Simon Says Math. And all of this stuff that I've talked about is there, plus everything else that you'd ever cover in a trigonometry course. Feel free to jump into those videos. And then I put out my email, simond3@mybrcc.edu. Feel free to email me with questions on any of those as well. But when you go to my YouTube page, Simon Says Math, click on the playlist and you can select trig, and then all of the topics are there. I also include videos of me working old tests of mine. And then Ms. Flanders and I have also done other workshops like these as well. We have links for those. Okay. Okay, so I'm gonna hit stop.